Hello and welcome, everyone. My name is RUTHRAN, and today we're diving into the fascinating world of crystals, specifically the beautiful cubic structures of sodium chloride, or what we commonly know as table salt. Before we dive in, let's have a look on what makes a salt. Sodium chloride is a classic example of an ionic compound formed by the electrostatic interaction between sodium and chlorine ions. Sodium, a group 1 alkali metal, has a single electron in its outermost shell. It readily loses this electron, achieving a stable electronic configuration, and becomes a positively charged ion, Na+. Chlorine, on the other hand, is a halogen from group 17. It has 7 valence electron and strongly attracts the one more to complete its octet. Upon gaining an electron, chlorine becomes a negatively charged ion, Cl-. The resulting ionic bond between Na+ and Cl- is driven by Coulomb's law, where opposite charges exert a strong electrostatic force on each other. This bond is the fundamental interaction responsible for the formation of sodium chloride. Now, let's look at sodium chloride's crystal structure. Sodium chloride crystallizes in a well-defined structure fundamental to solid-state physics. Its framework is based on a face-centered cubic, or FCC lattice. However, because this lattice includes both sodium and chloride ions, it is classified as a non-Bravais lattice. In a FCC structure, particles occupy the corners and the centers of each cube face, maximizing packing efficiency. The lattice achieves an atomic packing factor, or APF, of 0.74, meaning that 74% of the available space is occupied by ions. Sodium chloride forms two interpenetrating face-centered cubic lattices, one for sodium ions and the other for chloride ions. These lattices combine to create a highly symmetric and tightly packed crystal. Each lattice point has a basis of one sodium ion and one chlorine ion. The chlorine ion is located at half, shifted by half the cube's diagonal, while the sodium ion is at origin 0. Both sodium and chlorine ions have a coordination number of 6, meaning each ion is surrounded by 6 of the opposite types. The strong coordination contributes to the stability of the ionic bond. First up, we have the large container, our mixing salt solution, and two smaller containers. Now these will act as control environments for our crystal growth. And of course we need hot water in this to dissolve the salt. And of course we'll use a regular spoon to stir the solution. Well, it gets the job done, eh? We start by carefully pouring the hot water into the container. Next, add the salt into the water. Start by adding a small amount of salt at a time and be sure to stir continuously, and you'll see some undissolved crystals settling at the bottom of the container. This is when you know then the solution is saturated. Now, we need to filter the solution to remove any undissolved salt and impurities. Now, we'll pour some of the pure saturated solution onto a flat surface. After a few days, you should see some noticeable baby crystals beginning to form. These initial crystals are a good sign that the process is working. Now we're setting up our crystal growth environment. Take 3 container lids and position them on a flat surface. We will treat each lid differently to observe how evaporation and conditions affect crystal formations. The first lid will be fully exposed to air, allowing for maximum evaporation. For the second lid, we'll partially cover it by poking several holes evenly around the container for a more controlled evaporation. And the third lid will completely cover it. Carefully pick the best shaped cubes of crystal and scatter them evenly across each of the 3 lids. Each lid will have its own set of crystals. allowing us to observe how different conditions affect their growth. Now that the crystals are set on the lids, we need to place the entire setup in a stable location where it won't be disturbed. Make sure the area is cool and dry, free from any sources of heat and humidity that could interfere with the evaporation. Crystal formations begin with a supersaturated solution where there is more dissolved sodium chloride than the solution can normally hold. This creates a highly unstable state, ready to transition into a solid form. The first step in the crystallization process is nucleation. Here, tiny clusters of sodium ion and chloride ions come together, forming a stable nucleus, a seed that will grow into a full crystal. These nuclei serve as the foundation for the crystal lattice to develop. Once nucleation has occurred, the crystal begins to grow. Sodium ions are attracted to chloride ions and vice versa, thanks to Coulomb force. As these ions come together, they follow the FCC arrangement, creating a repeating pattern of alternating sodium and chloride ions. Evaporation plays a crucial role here. By removing water from the solution, the concentration of ion increases, pushing the system towards crystallization. Slow evaporation generally results in larger, more well-formed crystals, while rapid evaporation often leads to smaller, irregular crystals. First, let's examine the uncovered setup. As expected, the rapid evaporation caused by the exposure led to small, coarse, and irregular crystals. Now let's look at the fully covered setup. After 6 days, there was no noticeable crystal growth. This suggests that the lack of evaporation due to the sealed container prevented the solution from becoming supersaturated enough to initiate crystallization. Finally, here's the partially covered setup. With small holes poked into the cover, we achieved the best results, forming beautiful and well-formed cubic crystals. This setup demonstrates the importance of maintaining a steady evaporation rate. It allowed for uniform crystallization, giving us the perfect and ideal conditions to grow our salt crystals. Thank you all for watching and following along with the experiment. I hope this has given you a better understanding of crystal formation and the science behind it. I encourage you to try this experiment at your own house and see what results you can achieve with different setups. Wishing you all a Merry Christmas and happy experimenting.